Hey everyone, what's up? It's Pro here. Alrighty, and welcome to the how it works thing from the last video that I showed. Also, I modified some stuff to make this more like water, using an interesting trick for collision, since it would be extremely taxing to go over every single particle through like within every single particle. So how we're doing it is actually pretty interesting. It's we're reading the alpha channel of the current pixel that it's about to be at based on its x and y velocity. And if it's greater than a certain value, it triggers a collision response, which allows me to make adjustments. As you can see, very realistic water. A little too much foam, but you know. Also, that was interesting. There's like lines there. I wonder if that's only because, yeah, it seems like when I open OBS, let me lower the thread count here and the particles. Make it a little bit shallower, but you know, by lowering the thread count, it should free up some CPU for OBS. Oh, it's still doing it. Interesting. Huh. I don't know if that's showing up on the OBS side. Yeah, it is. Okay, I see it. But yeah, anyway, so here's how it all works. Oh, so satisfying. This is the module that makes multi-threading work. First, we're checking to see if it's using Node.js or not. Because if not, it bounds itself as a global variable called thread manager. So if you're using this in a regular browser or Node, both ways are fine. Okay, so we have a shares object and a workers object. The shares object is where all of the shared variables are going to go, like the particle array that contains the x, y, width, and height, or velocities. So yeah, that's where those are going to go. Oh, I love that so much. It's so dang hard to not get distracted by this. Anyway. Or was it? Yeah. See, that's what I mean. Like, I gotta stop getting distracted. Also, I need to update this. So, the get modules function. What this does, if you're using Node, then it'll just use Node fs to read the directory of the worker modules folder. Which, this is all the worker code, like the defaults of it. So you have assignKeys, you have an async iterator, or async interval. You have a base, you have reply. What these are all the functions that all the threads will have access to by default. So if you're not using Node, then it'll use fetch to like receive the file. However, it won't be dynamic because I can't figure out how to read a directory with fetch. And yeah. So what that does is basically it just appends the code with a little comment. So if I were to do this, you'll see a bunch of code here. You have the assignKeys.js, all the things that we just mentioned there. So the fixed string function basically just replaces the special commands, like for example in base, how I had right here. That allows us to tie the execution command that you define to a variable called exec, and we're going to be using that to determine like when or when not to fire up the thing. So the end results do not use IPC. However, in order to tell it what to do, we are using IPC. ICPs, we're not using the insane clown posse, dude. It's not. I guess it depends on the day of the week, but you know. Create a blob. How to do that is pretty simple. We just worker code. We just set this, and then we apply the get modules command. First, we convert the function that we're going to be tying into a string by doing you can do a function.toString thing. And the initializer is also a function, but we'll go over that in a bit. So, return URL object. Pretty simple. Basically what we're doing here is creating a JavaScript. We're creating a JS file within memory. So you don't have to have like a bunch of like worker codes and all that. You can just directly do it from whatever setup that you have. So constructor does nothing. But it's there because I don't know if I want to add anything to it yet or not. Alright, create shared buffer. This is where the magic happens. So you would let me pull up another. No, it'd be in buffers. Okay, shrink you. Matter of fact, I can hide that now. Okay. So first is the name of the buffer that we're gonna be sharing. Okay, then we have the length of the buffer. So we're using the particle length that we have times 4 because we need 1 for each variable within the key, within the object. For each key in the object. So we have x, y, x velocity, and y velocity. So therefore, we want to multiply the buffer length by however many items the array of objects has. And yeah, so how it works, we set the byte size to the length times the array type. As you can see, we're using a float32 array here. This is actually very important. You need to define an array type. So to get the actual rough estimated size, you need to do bytes equals the length that you define times the array type dot bytes per element. And the share is going to be a new array type. Notice how we're using the argument here as the type. That way you don't have to use like a bunch of different if statements, like if float32, if that. No, we just use it directly. New array type, and then a new shared array buffer, and then the size of being the bytes. Now we're gonna attach and or tie, whatever you want to call it. We're gonna attach it to this .share's share identifier. Now we're going to notify all of the workers to use that share. We're going to be doing that by iterating through each worker, and then sending the method share set with the value of the label share identifier and the data value of the share that we created. Now resize share, this isn't working properly yet. I don't know why. So it's weird. It just like completely erases everything. But maybe it's because, oh no, I am the big dumb. It is working. I forgot to like update I forgot to clone over the data. And then like reassign stuff. Okay, I'll fix that later then. So, this is how you call a function. So if we go to the module here that I have for particle updater, I'm making a function called initialize, which is the first, let's do this. Wait, what? Oh, wrong one. Listen, I'm smart, promise. Alright, so we have two things here. Initialize and command. The initialize is what sets up the variables that this is code that runs one time basically. As soon as the thread is created, well, as soon as it executes. So let me explain what's going on here. The assignKeys function. So assignKeys will take a large array. So like let's say, well, for example, let's do the particles here. Yeah, I can explain it without doing like a little comment art thing. Okay, so basically we're creating a key called particles. So now we can do particle.x.y, .x velocity and .y velocity. I'll go over how it works, but what this, like, and I'll show you the code in a minute, but what it does is a bit interesting. So note, if you remember how we multiply our particle share by 4 because each particle has 4 values. What this does is uses object.define property to artificially apply keys. Like, so .x will be every first number of every 4 within the array. .y would be the second number of every 4 within the array. So it's more, so when you access particles dot let's say index, so particle 50, and you do y, it's actually accessing the array, the share that we have, which is the particle array, but it's accessing index 50 times 4 plus 2, and that's like what y would be. X would be 1, or no, it would just straight up be that. Yeah, and then plus 1 equals y, and yeah, so it does all the confusing math behind the tables, and it allows you to very easily reorganize a transferred object. And the reason we need to do it this way is because JavaScript shared arrays, normally you can't, normally you can't do anything like this. You can only share values of an array, so you can't share objects. Like, you can't transfer x and y of something directly. So we use a little bit of a trick, and that's what all this here does. And yeah, that's basically what that does. So this is, like I said, this is an initializer, so we're going to initialize the thread's access variables here. Pixel, and what I'm doing here is the image data. I'll show you how I do that in a minute, but this is the update function. This is what happens every single time that it's ticked, that you call the tick function. This is the code that the thread runs at whatever timing that you want it to run at. So all I'm doing here is iterating through, I guess I can go over what I'm doing here with the percentage first. So I did a little trick here to interrupt to try and help with the synchronization. I did a little trick here to take note of the current time, and if it's longer than 0.6 milliseconds, then we're gonna break the loop, and then we want to assign a % variable here equal to the index. That way, after it gets called again, it's going to start from the from where it left off. It's almost what the async interval does here. But this is a bit more taxing, and it's meant for like other tasks, but I guess I'll go over it anyways. So the async interval you would use like this. You would say the objects that you want to pass through, and in our case, let's say the particles, and then rules would equal start and end. So there's what it starts at and then what it ends at, and then the name of the object that gets like applied to, so particle, and then the index, so we'll do I. So this is the iterator function here. So this is where you would say, like, if I is equal to n divided by 2 or something like that, you would do whatever you want. And we can do, you already have access to the particle in this case, so we'll do particle.x plus equals 1, blah, blah, blah. And then you have the yield function. So what this does So what this does here is, like, okay, after, oh, I forgot the timing. Stupid hair. That hair just came flying it. Okay. Now that that's out of the way, I had to pause there. The hair just like freaking drive-by'd me, dude. Alright, anyway. So, the interrupt is like how many... It's back. Okay, where were we? The interrupt. Okay. So, this variable here, it determines like when the iterator needs to interrupt and hang on. Okay, so kind of ironic, because that stupid hair. Anyway, so what it means is it tells the program after this amount of time, take a break, and then the yield function, the on yield is what happens when it does take a break. So we can say it halted at that, and the next tick, it'll continue from where it left off. And you have an on error as well. This will basically return the error. Listen, I'm good at explaining. So yeah, this is what happens when something goes wrong. You can kind of debug it if you want. And then you have an onFinish function. New particles. So while it will affect this array directly, it does return the object for some reason. I don't remember why I did that. But yeah, so this is when it's done. And that's how you use the async interval. It's a pretty powerful tool, but I didn't need all the on yield and stuff like that, so I just kind of bootlegged it with yeah. So how it works, by the way, is a generator function. More on those later. But basically, it's like a glorified version of what I did here, but a bit more powerful if you use it right. But also a bit more taxing on the CPU. So, yeah, the update function, what we're doing, iterating through where we left off. In this case, % is start, which is the default. And the start and end are based on a... here we go. Start and end are based on like what index the current thread... yeah, as you see here, we're iterating through the amount of threads that we define. In this case, 5. Or no, sorry, 12. That's our resolution divider. Yeah, we're setting the shared variable time or thread limits, which we define here. As you can see, thread limits, we're assigning keys for the workload. And we just have thread values .length times 2. In this case, I need to recalculate that actually. Anyway, and yeah, that lets us iterate through. Why am I having such a confused moment right now? So anyway, how each particle works, I'm not using that for some reason. Oh, that's right. I got rid of the X check. I'll get rid of that. So how this works: next particle y is going to be set to the current position of the particle, and then added by the velocity of the particle. I was flooring this, but I guess round would be better. Yeah, we're going to round that, and then we're multiplying by the screen width plus rounded of the particle x, and then multiplying that end result times 4. that'll because each RGBA basically. Very similar to the particle index here, except we don't include any of the velocities in the particle index. So that allows us to find out which pixel on the screen it should be rendering to based on its position. And then 0 would be the red channel, 1 is the blue channel, 1 is the green channel, 2 is the blue channel, and 3 is the alpha channel. So that's how that works. That's how that draws to the screen there. And we increase the Y velocity a bit here, set some mouse effects. Trying to remember if I optimized it because I know I was going to, and I was like, okay, well, anyway, this is how it like attracts to the mouse. I'll go over how the mouse events are sent in a bit. Yeah, so then we do if the particle, so if the alpha of the particle that it's the position that it's going to be in is greater than 180, which means there's a few pixels, there's already a few particles there, and its Y velocity is greater than 0. There we go. The unformatting was like bugging me. What it's gonna do is we're gonna set a value called adjust equal to the Y velocity. You're gonna let's try this. Nah, I ain't gonna get all complicated with it. So this is just how much that it bounces back. So I just have it like an absolute value, and I set the Y -1, but yeah, I guess that's still okay. So what we're doing, what this does is if the adjust value is lower than 1, it'll make it so that it always uses 1. And then the math.abs function is an absolute function, which means it always returns a positive version. And here I set the x velocity. I kind of adjust the x velocity by like a random amount to make it simulate the whole bounce thing, like splash, like for the left and right directions and stuff. And then we're gonna check and see if the Y velocity is less than 0.1, and if it is, we're going to multiply. Oh yeah, by the way, the abs of that. Yeah. They don't need abs actually because we're already checking if it's above 0. Free up some CPU resources there. And if it is less than 0.1, we're going to multiply it so that it's always moving, basically. So the wall bouncing here, pretty simple. We do particle.x if it's less than 0 or greater than the screen's width. -1, by the way, because if we don't do -1, it is going to update the particle's x and y position like improperly, and you're going to end up with I need to -1 that as well. Like the particle is going to go off screen a hair pinch, like a little bit, like either to the left or the right. And matter of fact, let me do one here. Yeah. And if it does, then the index processing here will just go to the next index, which means a particle that's like 1 pixel off screen to the right will end up being rendered at its Y position +1 at an X of 0. So it'd just be like, you would have like these particle lines on the sides. Here we're checking to see if the time is greater than 16.6 milliseconds, and if so, we're breaking it. We're interrupting the loop. So if % is equal to n-1, which means it's done, like that's how we tell if if it's time to reset the percent variable. And if it is, we set it back to start. And we post a message here saying done. And we want to do that because we have a count here. Now this is the update function here. So the tick function, what this does is it kind of sets an interval. You want to use intervals instead of request animation frame for this. And the reason for that is because request animation frame will throw off the synchronization big time. And I don't know why it does. Somebody, I'll leave that up to somebody else to figure out. So we're using a standard set interval. Well, I guess you could use request animation frame. Yeah, you just need to use the delta time thing. But anyway, so we're iterating through every updater, which I'll go over what that does in a minute. And this is basically the workers that we're creating here. Like the workers for these functions here. So we're iterating through, and we're calling the tick function, which is what allows it to run this code here. And if the screen is clearing, we're gonna empty the image data buffer. We're gonna set it all to 0, and then we're gonna set clearing to false and count back to 0. So the function begin. This is the thing that begins the worker. You don't say. But yeah, how it works is we pass the worker through, because this is going to be the this is what the function will end up returning. So it returns the worker. So then we call the tick function at the very start, and then we have an on message event here, worker.onMessage. We don't really care about the data type, but it's there if you want it. So what we're going to do basically is, okay, yeah, no, I thought I was like clearing it twice. So like, what? All right, anyway. So what we're going to be doing is if the count is equal to the threads, which means it's done, like every thread is rendered, then we're going to set the screen.clearing to 1. And this needs to be 0, by the way, because screen clearing is also passed as a share. And we're going to set the image data variable here. This is the shared, not the shared, this is the actual image data that's going to read from the share. So we're setting that equal to the main.shares.image data, and then we're putting that data directly into the context that we have set up. And that allows us to draw the particles. I left this in and didn't, yeah. Well, I left one of the request animation frames in because, like, when I was playing with it, I was trying to get it to work right, but anyway. So, back to the app here, the main thing. This is how we're spawning them. At the very start, we grab the module that we had. Of course, if you're doing this in regular JS, you would obviously do it different, but yeah. Most important thing is that we have our init, update, and begin function that we went over here. And finally, now we are going to iterate through all the threads, and we're going to set the max threads. Why did I do that? Ignore that. Count, we're going to set equal to particles.length. Matter of fact, that can also be outside. I2 is equal to I. Why did I do after this? Alright, anyway, this is why you clean up before you make videos. Alright, anyway, I promise I'm smart. Get rid of that. We don't need that anymore. Anyway, back to the... So we're setting the shared thread limits of the index of the thread that we're on equal to start and end, which is, the start is equal to floor I divided by threads times count. And then the end is equal to floor I plus 1 divided by threads times count. And the reason we want to do that is because, am I doing that wrong? I think I am, because yeah, I think like this, some particles are gonna, like, some threads are gonna process one. So like we'll probably have a few particles that are like double updating, which is an issue, but I'll fix that later. So yeah, we're setting that to that, and we're calling the task. You know, I actually need to, yeah. So what we're doing, main.task, the init function that we had, the update function that we had, and then it's an async function, so we're gonna do .then. So like whenever it's done, you can catch an error if you want. Yeah, so the .then, we're gonna call the begin function, the one that we've seen here. So we're basically calling all three of these here, not the tick, but yeah. And that's going to make the thread run all this stuff. And that's pretty much all there really is to it. For the particles though, I'm just setting the values, like initial x, initial y. I'm setting the velocities and all that. Now, oh dude, I think I know how to fix this. Auntie? What? Maybe data copy equals main dot shares dot image data. And after we do the resize, we're gonna do main dot shares dot image data dot fill. No, that wouldn't work, would it? Okay. Coding in real time while explaining, that's great. Okay. So data, yeah, if data copy I, then yeah, how would I do that? Like with the width? Well, I guess we wouldn't have to. Yeah, I would, because otherwise X particles will be in like weird positions. Oh well. Oh, yeah, no, I know what to do now. Const O screen size equals screen not width. O screen W and H. Whatever, I'll figure that part out after, so I'm not gonna worry about this right now. This is the thing that resizes the canvas and everything, and it's supposed to resize the image data as well, but that's where it breaks. But if you don't do that, then it'll always think that the width and height, it'll always have the width and height of the original as its limits, and it's gonna break, and it's gonna be all kinds of jank. So for now, yeah, we just have the on resize event. That's basically all there is to it. Let's see, what did I go over already? I went over these, went over shared buffer, resize share. Went over the task. So here's how the task works. It returns a promise, which is an async thing, so you can do the .then or .catch. It tries to create the blob here and and use that as the worker code. And then we have a few functions that we're defining here. .destroy. I can clean this up as well, but the .destroy function basically terminates the worker and it deletes it, like, from the memory. It tries to anyway. We have events. Let me clean this up as I explain it. So the events are pretty much exactly like the original events. It just allows us to do dot on instead of like forcing to do dot on message, dot on this and that. Yeah, and it's pretty much how it works. I don't know how to explain. We're just adding to the event array here, and then when we do have a message, it's going to iterate through all the on message events that we have stored. So you can do like multiple things. So the worker.tick is a function that posts a IPC message telling it to execute the method tick. And for label in this .shares, so as we create a worker, it's automatically going to iterate through all the shares and apply them to the worker thing. Then we're going to do workers.push worker, and then we're going to resolve the worker, and that's how that gets sent to the .then function. So the assignKeys, interesting how it works. So we have the data, like of our share, which is the giant array of values, and what was I using result for again? Oh yeah. All right. So the chunk size is the variable names.length. So the variable names is what you define as here. So x, y. So now the value here that we're setting, part data, will have it'll always return an array. So you can like define the index of the item that you're looking for, and it has to do that because of the way that the shared array buffers work. It's confusing, but moral of the story is we're just going to iterate through the length of the data, which is the share we went over, and we're going to increase it by the chunk size. That's because we don't need, like, yeah, we want to make sure that each index is its own thing. Oh man, I'm having a really difficult time explaining this, but basically we're setting a chunk equal to the variable names.reduce, which basically it's kind of like a dot map or a dot or like a dot for each, but basically we're setting the ACC value, which is the key name, which is a temporary thing here. How can I explain this better? Anyway, we're assigning a key to the shared label, which is the thing that we're accessing, and we're setting it equal to I plus j and then j. Why it's like that is a very complicated. Well, it's not very complicated. I'm just really bad at explaining it, but I may explain this better in another video. But yeah, so the assignKeys, that's how it does. That's how it works, and we're using object.defineProperty, so that when we say this like value that we're setting .x or .y, it's going to point to the share at the index, which is going to be the I plus j, which is the variable name plus the index, like of the property, the key. And yeah, it's going to be set to the value. So now we can the set, what it does is it allows us to do thing 0.x equals value, and then the .get, what that does is allows us to return. So like we say console.log thing 0.x, for example. So we're going to push that into a result array, and after all that's said and done, we're going to return the results, and then that will create an array of objects that have these key values. and stuff. So that's how we transfer. There's a lot of math like behind this, but yeah. Now we just have some getter functions here. This gets all the shares and workers. You can do just get shares to get the shares, or just get workers to get the workers. And that's pretty much it. By doing that, we make sure that we do main.assignKeys to assign information about the particles in case we ever want to debug. I don't know why I left that console log in there. And yeah, when all said and done, or all having, I don't know where I was going with that. Okay, so yeah, this is what I mean by it breaks. You just gotta reload it once, because when it initializes, the debug thing opens up. But yeah, that's what makes this. Oh yeah, I was gonna go over how the mouse worked. Alright, so how the mouse works. There it is. You can get rid of the blurred variable. I'm not using that anymore. So for the mouse, we're assigning the buffer thing here that we had. What is it? Yeah, right here. And we have 3 values here. And that's the X, Y, and the button that's being pressed. So we only need those 3 for that. This can... Yeah, I want to keep it a UINT 16 because... Yeah. And so yeah, after we make all the buffers, we're going to assign mouse X, Y, and active. I don't know why I called it active, but then we just have standard event listeners here. Every time the mouse moves, the mouse.x and .y, which is the share index of 0 and 1, will be set to the page, like the Y position that it's at on the page, and then like also including, hang on, not including, but dividing by the resolution divider here. What's up? Okay. So when a mouse button is down, we're just assigning the button +1, and that's because like we want active state to be 0. I don't remember why I did button +1 to be honest. And that allows us to, in the worker here, we're going to assign keys to the mouse share, the same things that we did. Notice how we're doing a 0 at the end of that, and that's because the assigned keys will always create an array. So it's so if you only have like one entry, then you just assign index 0 to the thing that you're assigning it to. Listen, I'm good at tutorials. All right. Anyway, yeah, and then we want to do this here. That way, it doesn't color like outside the screen too much. Well, I guess it wouldn't. Yeah, we can get rid of that and save up some resources. Yeah, it should be fine. Yep. Because we had our limits down there. I forgot all about that. Okay, so if mouse.active is greater than 1, which means like if you're pressing right click, 1 is left click, 2 is right click, and 3 is like middle click. So if you're not pressing left click, it's going to repel the particles, but otherwise, the heck? Can you like not highlight everything that I'm on? What is happening? Whatever. Anyway, so yeah, we have our distance here that we're going to, matter of fact, I can make this a little bit more optimized as well. Yeah. And before I break it. Yeah. So what we're doing, if the distance is greater than itself, and the reason I want to do that is because like you don't want them all to group into one like concentrated spot. So I'm setting their minimum and maximum distance based on the index of the variable, of the particle. I mean the thread. Not the particle, the thread. So the $ index is the index of the thread. I guess I can, yeah, go over that. How do I... Where am I defining it? Oh, yeah, no, it's... I close it. It's in here, it's right. I defined it at the header of that. So upon the creation, we set the index to the worker length. And, yeah. So we're checking to see if it's greater than that, and if it is, we simply add the x velocity and y velocity by the destination x and y, which is the mouse position, compared to itself, multiplied by the damp factor. And the damp factor, basically, if we don't do this, it'll like instantly absorb to it like this. Oh, that's pretty cool. Whoa. Ooh, that's fun. Anyway, not getting distracted. Yeah, and the damp factor basically acts like a divider of sorts, and it makes it so that it like transitions into that position rather than immediately snapping to it. As you can see, it makes it all like orbity and like wavy and stuff. Dirty mouth, clean it up with orbit. Wow. Anyway. Oh. That was interesting. Yep. I think I covered everything. I'm trying to think of anything else that I did not cover yet. I think I went over everything now. I mean, other than the screen size, which we have width and height, and then we have a clearing value, and that's updated on our request resize function here. Yep, I think I covered it. Sorry for the dollar store of an explanation thing, but yeah, I'll comment the code and everything like a bit better before I post it on Git. Yeah, and if you look in the description, you will find the Git for this. If it's not there yet, then it will be soon. I guess I can go over how I did the foam. Yeah, I didn't cover that yet. So how I'm doing the foam trick is just a little bit of math here. So I'm setting the red value equal to the absolute between the x and y velocities divided by 3. I guess technically we can do 5, but it might be a little too blue. Yeah. I got you blue. You want yellow? She doesn't want yellow. Blue and yellow? No. Anyway. Yeah, so basically the faster that it's moving, the brighter it's going to be. Because I'm setting the green equal to the same thing as the... as 1.5 times the pixel index of the red. So, I mean, pixel index. The value of the red. So red and green are going to be adjusted by the velocity, basically, of the particle, and that makes it so like it looks like foam, like when it's moving a lot. Matter of fact, could probably make this a little bit more interesting. Hold on, let me. Nah, this is gonna look ugly, isn't it? Yeah. Anyway, yeah, so that's how it works. Pretty fun. It's like really addicting to. Did I go over how the thing works yet? How here? Yeah, I did. If you lower this, like say 80, it's gonna go all kinds of ham. It's gonna like all stick to the top because it's bouncing off of each other like constantly. Oh, I guess it will settle eventually. Oh, that's pretty cool. Ooh. Adjust that a little bit here. Perfect. 144 it is. But yeah. I guess that makes it more fluid-like. That's interesting. Again, though, we're basing off the alpha particle, like... Alpha particle? What? We're basing off of the opacity of the current pixel that it's going to be at. In the X, or I mean, in the Y position here. You can do the same thing for the X if you want, like make it kind of collide with each other horizontally and launch itself like randomly after that. But it can get a little bit chaotic, and it's not really needed for this little demo thing. So like the less resources that we can use, the better. But yeah, so this can run a lot of particles. Where's my... Let's try to run 40... let's do 31,000, because we're using 12 threads. Oh my lag. Well, it's a bit slower. Also, the more particles, the more full it's going to get. It's like, you know, kind of like how real containing would... I don't know what I'm saying. I'm just looking for a dang excuse to play around with this more. So if I like double the... or like not double, but if I increase the resolution divider, it's going to get too full. There we go. All the resolution divider does... Was he stuck? Anyway, I'm done. I gotta stop. I'll just keep this video going, just playing around with particles.